Hello, everybody. Happy St. Patrick's and St. Joseph's Day. I have been waiting a while to give this particular video because I wanted to finish a program that would make it easier for me to explain it. Now, in the last video, we talked about the Dijkstra algorithm. In the Dijkstra algorithm, you know everything, and you just start computing locally to compute the shortest path. The other algorithm that I mentioned that time was the Bellman-Ford algorithm. And this particular video is going to do an example of the Bellman-Ford algorithm. Now, there's the very small little network I used, and you could represent it as a table that way. I used infinity, as I think the book does, or most books do, but when I programmed it, I had to make it 100. There are two ways to put it in. I could have tried putting it in as a table, or I could have tried a different form. I used a different form. In fact, here's the file I use for input. The way you read this file is, A is my first node, and it has 3 neighbors. Its neighbor B, the distance is 4 from A. Its neighbor C, the distance is 5 from A. The neighbor D, the distance is 1 from A. Then, the second node is B. It has the second node is B. It has 3 neighbors. Its neighbor A is 4. Its neighbor C is 1 away from it. Its neighbor E is 4 away from it. Then C has 3 neighbors, 1, 2, 3. D has 1 neighbor, A. E has 2 neighbors, B and F. And F has 2 neighbors, C and E. I can bring this down so you can take another look. It doesn't want to come up. There it is. And you can see that I tried to get it in. For example, here's E going to F at 5. Here's F going to C at 4. So that was the way I put it in for reading. Now, here's what I got. At first, the initial conditions are that each of the nodes has its own table. The table has 3 columns in it. Here are the 3 columns. At node A, I list each neighbor, B, C, and D, and I tell you what the shortest path is to that neighbor. Now, I shouldn't have used the word neighbor. I should have used node, because this is only for the first time that I use the word neighbor there. So this is saying that A has 3 neighbors. And if you want to get to B, you go through B, and it's a cost of 4. If you want to go to C, you go through C, and it's a cost of 5. And the difficult thing about explaining this algorithm is there's so much that you have to write down. That's why I needed a program. For example, I need 6 tables here. And you can see I've got them there. And that's okay. Now, what's next? This next section, I better put it here. This is the messages exchanged between nodes. So in each case, I have who the sender is, who the receiver is, and what is sent. So A tells B, and I put 100 in instead of 0, which is what I think I put up here. I put 100 because it made it easier. It worked better. So I don't care about A to A. A to B is 4. A to C is 5. A to D is 1. I don't have a way to E. I don't have a way to F. That's 100. Now, A to C, I sent the same information. A to D, the same information. C to A, now I had to copy C's table from what I had. And I did this. There are 36 of these. No, pardon me. There are 30 of these. So you can see where it gets complicated fast. Now, I made the exchanges. What new news did I get? Well, let's take a look at the graph again. What does A find out? Well, A learns from B that B has a neighbor E and a neighbor C. A learns from C that C has a neighbor F. So A now has a way to F and now has a way to E. So we'll see what happens. It should change. So let's look at the table now at A. A is now, I can get to E for 8 and I go through B. I can get to F for 9 and I go through C. If you look at the links, they add up properly. All right, that's round 1. I don't know if it's done. I know, for example, table E doesn't have everything. And I noticed that table D doesn't have everything. So I run it again. I make the new exchanges. And I go from there. Trying to keep everything together has never been easy on this. Let me get that back. And go here. Try to get it down there so it'll all be on the same page. Or the same column, I guess I would say. It's not going to be perfect, but we're getting better. I think if I move this, I probably will have it well enough. And then I have to move this. And I think you can see there would be an awful lot to do by hand. Now, after round 2, well, there's a bigger change here. That path 8 that went down to E, it's okay, and it is going to stay. But now the path from A to F might have been 9. Oh, the path I really worry about is the path from B to F. B to F through E isn't going to work. B to F through C is going to work. So let's see if that's what it did. It said that if I want to go from B to F, I should go through C. So this just keeps going like that. I went 5 rounds because you're not going to get 5 rounds covers every single node. I got to have steadiness by then. So that's the Bellman-Ford algorithm. What can I say about it? Well, first of all, it requires a lot of exchanges of messages. Every round, you have to do an exchange. And every 2 nodes, every 2 neighbors have to make an exchange. Then they have to update their tables. Now, it turns out that there are the two algorithms, Dijkstra and Bellman-Ford. One is used internally, and one is used for the backbone network, or the network outside the small autonomous network. So they're both in use. And I'll show you that when we get down to the more specific algorithms that are used. That ends talking about how roots are computed. One thing you should know and have to know is that the root might change. For example, right now I am getting 2F from A through C. But what happens if this node between C and F dies? It's conceivable it could happen. Well, that will mean that C will say, I need a way to F, I don't have one anymore. So it'll ask its neighbor B. And B, unfortunately, will say, I can do it in 5. So C will think it can do it in 6, because it goes there and there. But it turns out that B is using that node, that broken one too. And they'll go back and forth until finally B says, it's too long getting down there, and B switches to the root through E. We'll talk about that next time too. That's called the countdown to infinity. It's in the book. You can take a look at it. But the point is, I remember to make right now is that roots can change. They're not fixed. And these numbers may represent anything. They could represent the cost of the link. They could represent the speed of the link. They could represent the congestion of the link. In fact, in some cases, in the real world, a link is marked as don't take it because it'll cost me too much. For the two networks can agree on a reasonable price to take one from one network to the other one. So the networks use a different network, even if it's more expensive if they run the algorithm. So that's why there's a different algorithm. There are different things that happen in algorithms. It isn't always as easy as just looking at the link. The link could be poisoned because it would cost too much. So that's it for now. I will be trying to send you one soon. I am very strongly thinking of giving you as a project to write this program that I wrote. It is not horribly hard, but you do have to keep your toes about you. And I think you need classes to do it. I wrote a class that was a node, and I wrote a class that was a message that's exchanged. And then I used both of them in setting things up. And it worked well. I don't know if I could have done it more easily. I did have a few kludges in my particular way of doing it. If I wrote it again, I probably would do things differently. We'll see you later now. So long.